Welcome back everyone. In the last lesson we have seen different kinds of numerical methods to find out the roots of an equation. So from this lesson we will start our numerical methods, and first of all we will see the bracketing method, and under this category we will see the bisection method. So in this lesson we will go through the details of bisection method to find out the roots of an equation. So we have already seen that graphically in most of the cases the function changes its sign in the vicinity of the root. So that's the basic criteria of applying the bisection methods. So what we do in the bisection method, we initially assume two separate points to locate our boundary, and within that boundary we assume that there is a root. So that's the first step of applying the bisection method, that we have to guess two initial points to define a boundary. So let's say those two initial points are xu and xl. xl is the lower boundary and xu is the upper boundary. So we assume that there is a root within these boundary, within these 2 points xl, x lower and x upper. So the corresponding function values at these 2 points are f of xl and f of xu. So we initially told you that the function changes its sign at the vicinity of the root. So if there is a root within these 2 points, that means the function should change its sign at any point within the boundary. So what we see that f of xl and f of xu should have opposite signs. Why? Because we have assumed that there is a root within this boundary, and that if there is a root, the function should change its sign, and that's what we have assumed, that f of xl and f of xu should have opposite signs. So if we multiply these two values, f of x lower and f of x upper, the value should be less than 0, because one should be negative. This is our first step of applying bisection method. So we have seen this graph in our previous lecture, that at the vicinity of the root the function changes its sign. So that's how we initially approach the bisection methods. So bisection method is also known as binary chopping or interval halving or Bolzano's method. So all of these are different names of the same bisection method. So there are different cases that we will see within this category. So what we do in this bisection method, that we initially assume a boundary, and we step by step we reduce that boundary, and at one point that boundary converges to a point, because the length is so small that the boundary looks like a point, and that is our root, and that's our final root. So let's look at the algorithm that we are going to use to apply the bisection. So in the bisection method algorithm, in step 1, we have already said what we need to do. We need to assume two separate values, x lower and x upper. X lower is the lower boundary and x upper is the upper boundary. So within this boundary, we assume that there is a root located at any of the point. So at those 2 points, if we say there is a root within this boundary, so that means if we calculate the function value at those 2 points, the values should have opposite signs. That means f of xl and f of xu should have opposite signs. One should be positive and another should be negative. So if we multiply those two values, f of x lower and f of xu, the value should be negative. And that's the first criteria of applying bisection method. That's our first step. We have to be confident that these two values, that means the multiplication value, should be less than 0. And if that is the case, we can almost 100% assure you that there is a root within the boundary of x lower and x upper. So this is our first step. In the second step, we approximate our new root based on the value of x lower and x upper. So how do we calculate that? We just calculate the mean of those values, mean of those boundaries. So look at this. This is the mean value, x lower plus x upper divided by 2. and it is termed as XR, and this XR is our new estimation of the root. Although it is not the root, we are just approximating that this is our root based on the values of X lower and X upper. So this is our estimation for the first iteration. So based on these calculations, we can go to the step 3. So we will have 3 separate cases. The first case, if f of xl and f of xr are situated on the on opposite sides of the root. That means if we multiply these two values, f of xl and f of xr, and it turns out to be less than 0, that means both f of xl and f of xr are situated at opposite sides of the interval or opposite sides of the root. So if this is the case, what we do, we reduce the upper boundary. We reduce the upper boundary to the new approximate root, xu equal to xr. So once we reduce the upper boundary, our new boundary is x lower and xr. And with this new boundary, we return to step 2 and recalculate the procedure. That means that's the second iteration. But if this is not the case, if we have other cases, so what we will do? In the second case, if f of xl and f of xr, if we multiply those two values and it turns out to be greater than 0, that means f of xl and f of xr have similar signs. If similar signs, that means if both of them are positive, their multiplication would also be positive, that means greater than 0. If both of them are negative, their multiplication would also be positive, that means greater than 0. That means f of xl and f of xr now for this case are situated on the same side of the root. That means they are of similar sign. So if this is the case, what we do, we increase the lower boundary. That means we set xl equal to xr. So once we do this, our new boundary is xr and xu. So with this new boundary, we return to step 2 and we recalculate the steps. There is a third case where f of xl and f of xr, if we multiply those two values, it turns out to be equal to 0. What is this? That means f of xl and f of x are now situated on the same location. What we mean by this is that we have already converged to a point where the boundary is so small that the multiplication turns out to be 0, and that is our root. When this is the case, there is no other calculation needed, and this new xr is our desired root, and at that point we can terminate the computation. So practically in most of the cases we will not encounter the third case, because third case is the sure shot of our finding root. We might not encounter the third case, that both f of xl and f of xr is situated on the same at the same point. So what we do in practical cases, we approximate the error within separate iterations. That means, say for example, in the first iteration we get an estimate of the root xr. Similarly, in the second iteration we get an estimation of the xr as well. So if we calculate the approximate error, the approximate change of these new estimations of the root, and if we set up a boundary or a criteria to terminate the computation, at some point the error would be less than our predefined error limit, and at that point we terminate the computation. We have already encountered such case. For example, we used the approximate error, where the approximate error percentage error is denoted as something like this: xr new minus xr old divided by xr new. This xr new is the current approximation of the root at the current iteration, and xr old is the approximation of the root at the previous iteration. And if we calculate the approximate error, something like this, and at some point this xa would be less than any tolerance limit epsilon s. So if this is the case, so where at some point epsilon a, that means our percentage approximate relative error, is less than our predefined limit epsilon s, then we terminate the calculation. So that's the basic criteria that we use in our practical course or examples. So we have seen the algorithm and the termination criteria of bisection method. Let's look at an example so that we can be more sure of what we are doing in the bisection method. So let's say we have a function f of x equal to x square minus 8x plus 12. So our question is to find out the root of these equations using bisection method. So what we need to find any a value of x for which these function value turns out to be 0. So that is the definition of finding root. So what we do in the first iteration, as we say, in the first step of our algorithm, we need to predefine our boundary. That means we need to set a boundary x lower and x upper. We have to assume that. So say for example, we assume x lower is 1 and x upper is 4. So what we mean is that there is a root within these 2 points 1 and 4. So we are assuming that. So we need to verify our assumption. So how do we verify our assumption? We find out the values of f of xl and f of xu. That means we find out the function values at these 2 points, x equal to 1 and x equal to 4. So if we insert these two values in this function f of x, we will find out the values of f of xl, which turns out to be 5, and f of xu, which turns out to be minus 4. So look at the values. F of xl is positive and f of xu is negative. So if we multiply these 2 points, f of xl and f of xu, it turns out to be less than 0. So our assumption is verified here. Look at this. Our function values are of opposite signs and the multiplication result is less than 0. That means we surely have one root, at least one root within these 2 points 1 and 4. So we initially assumed one thing and then we verified that assumption, and we now know that at between these 2 points there is a root. Now we have to calculate further to find out the specific root. So how do we calculate? So in the first case, we find out our new approximation root xr, which is the average value of our boundary, and our boundary is 1 and 4. So if we take the average of these 2 points 1 and 4, we will get 2.5. So these 2.5 is our new approximate of the root. Okay, this is our approximation of the root, first approximation in the first iteration. So we find out the value of the function at this new approximate point, that means f of 2.5, which turns out to be minus 1.75. So next we go to the third step of our algorithm. We have f of xl, we have f of xu, and we have f of xr. So based on these 3 points, we need to choose a criteria, choose a category from the third step of our algorithm. So let's see what we get if we multiply these 2 points, f of xl and f of xr. If we multiply these two values, f of xl, which is 5, and f of xr, which is 1 minus 1.75. So if we multiply these 2 point values, we get minus 8.75, which is less than 0. So if f of xl times f of xr is less than 0, can you remember what is the category that we find out that we can match in our algorithm? This is the I guess our first category. So if this is the first category, minus 8.75 is which is less than 0, then what we do, we reduce our upper boundary. So what we have in the upper boundary, initially our upper boundary was 4. Now we set the upper boundary to our new approximate root, which is 2.5. So now we have initially we had a boundary which is 1 and 4, but now after the first iteration we have the boundary which is 1 and 2.5. So with this new boundary we step into the second iteration. So after first iteration we have the boundaries x lower equal to 1 and x upper equal to 2.5, which is the first approximate root in the first iteration. So next we recalculate our procedure. We find out the f of xl and f of xu, which is now in this case 5 and minus 1.75. And if we multiply these 2 points, we will see that 5 into minus 1.75, which is less than 0. That means now, that means till now we have a root within our boundary. So remember this, in the first iteration we already checked the multiplicative result of f of xl and f of xu. So if in the first iteration it turns out to be less than 0, that means the function values are on the opposite sides of the root, then we never need to recalculate that criteria in our later iterations, because in the first iteration we already verified that. So throughout our example, throughout our algorithm, that verification is going to hold. So we don't need to re-verify that condition that f of xl and f of xu are on the opposite sides of the root. We don't need to re-verify that in our each iterations, in our successive iterations. So in this case, now we approximate our new root, which is the average value of our boundary, and our boundaries are 1 and 2.5. Then if we take the average of these values, it is 1.75. So this is our new approximation. In the iteration 1, this approximation was 2.5, but in iteration 2, it is 1.75. Next, we calculate the f of xl point, that means which is 1.0625. Then we turn down to our third step of the algorithm. Before turning out to the third step, we need to calculate the approximate error, which is epsilon a. That means now in the first iteration we did not calculate the epsilon a, because at that iteration, in the first iteration, we did not have xr old. There was only an xr, the first approximate value. But in the second iteration, we have the approximate root of the second iteration, which is xr new, and we have the approximate root of the first iteration, which is xr old. So now we can apply this formula epsilon a, so which turns out to be 42.857%. That means we have an error, approximate error of this percent. That means we are not near the our convergence, so we need to use further iterations. So to get to our next step, what we do, we calculate the multiplication of f of xl and f of xr, which turns out to be 5.3125, which is greater than 0. Greater than 0. So what we mean is that both f of xl and f of xr are of similar sign. Look at this, both have similar signs, 5 and 1.0625. Since both of them have similar signs, that means there is no root if we take these two boundaries xl and xr. So we have to take the other possibility. That means we have to take the boundary which is xr and xu. Since xu is already there, which is 2.5, we need to change the xl value. So in this case, if we look closely, this is the second criteria of the third step of our bisection algorithm. So at that step, what we did, if this is the case that f of xl times f of xr with greater than 0, we change the lower limit. We change the lower limit to our new approximation 1.75. So once we get our new boundary, so which is in this case 1.75 and 2.5. So with this new boundary definition, we move on to our third iteration. So in the third iteration, after the second iteration, we have our new boundary, which is 1.75 and 2.5. So we recalculate the values of f of xl and f of xu, which is 1.0625 and minus 1.75. Look at the values, look at the signs. One is positive and one is negative. So by definition there should be a root within these 2 points. Since we already verified that in our first iteration, we don't need to re-verify that in our current iteration. So we directly calculate our new approximation of the root, which is the mean of the boundary, which is 1.75 and 2.5. If we take the mean, we will get 2.125. So this is our new approximation root for the third iteration. So before proceeding further, we need to calculate the approximate error. If the approximate error is lower enough, then we can terminate the calculation. But if it is not, we have to recalculate further. So to calculate the approximate error, we need to find epsilon a, which is xr new minus xr old divided by xr new. Xr new is our current approximation of the root, which is 2.125, and xr old is our previous approximation of the root in the last iteration. And in the last iteration, that means iteration 2, this root was 1.75. Here 1.75. So if we insert these two values in this formula, we will get an error to be 17.6%. In the second iteration, we had this error to be 42.857%, but in third iteration, we have 17.6%. Although it is lower than the second iteration, but still it is very high. So we need to recalculate further. We need to calculate further iterations. So to get to our next iteration, we need to find our new boundary. We already have the boundary 1.75 and 2.5, that is for the third iteration, but to move on to the fourth iteration, we need to calculate our new boundary. So how do we calculate our new boundary? First we calculate the f of xr, which is minus 0.484375. Then we multiply f of xl and f of xr, and if we see their multiplication is now negative. If that is negative, it is the first criteria of the third step of bisection algorithm. So we change the upper boundary location from 2.5 to 2.125. So this is our new upper boundary, which is 2.125, and our lower boundary is kept whole, which is 1.75. So what we do, we move on to the fourth iteration. Since our approximate error is not up to the mark, so we have to recalculate further. So in step 4, we have the new boundary 1.75 and 2.125. We have got this result from the third iteration, from the previous iteration. So we recalculate similarly f of xl, which is 1.0625, and f of xu, which is minus. So these are of opposite signs. We don't need to re-verify that since we already did that in our first iteration. So we directly get our approximation of the root, which is 1.9375, and we take the we calculate the epsilon a, that means our approximate error, which is 9.67%. Look at this, it already got lower. In the third iteration it was 17 point something percent, but now it's 9.67%. So it's already lower, but still this error is very much high. So we need to recalculate further. So let's say we move on to our fifth iteration, but before moving on to the fifth iteration, we need to recalculate our new boundary. So how do we recalculate our boundaries? Similarly, we multiply f of xl and f of xr, which turns out to be positive. So since this is a positive value, that means both xl and xr are on the same side of the root. So that's why we cannot get these 2 points to be our new boundary. So what we do, we change our lower boundary to 1.9375. Since at xr 1.9375, this value is positive, but at xu, f of xu, it is minus 0.484375. So these two values are of opposite signs. That's why we take these two boundary points. That means 1.9375 and 2.125. So that is our new boundary definition for the fifth iteration. So similarly, we calculate our fifth iteration and we will get a result. Look at this. The result is the error is lower, even lower than the fourth iteration. In the fourth iteration, it was 9.67%, but in the fifth iteration, it has reduced to 4.615%. So if we recalculate further, this error would decrease further. So we can guess that. So that's what we are talking about bisection method. We calculate further and further through iterations and iterations until our approximate error reduces below a certain limit. So think about this. If we had set our limit to 4%, that means I'm sorry, if we set our limit to 5%. So already in the fifth iteration, we have got an error which is less than 5%. So if in our case, our predefined specified error limit was 5%, we would have stopped at the fifth iteration. So that's how we calculate the bisection method. And I hope you already you were able to grasp the bisection method, how we calculate the iterations, how we calculate the approximate error, reduce the boundary conditions. So I would suggest you to look at the algorithm further, specifically the third step of our algorithm. Please go through that step. If you graphically visualize the third step, I think it would be clearer. So obviously we are not going to use these bisection methods by hand. We are going to use those in computer methods. So if we are going to use computer code, MATLAB codes or any other codes, programming languages, then we would have set these limit not 5% but rather very much lower, let's say 0.01%, so that our calculation is much precise, much more precise. So that's what we will do in our practical examples. So obviously this bisection method is the most basic of bracketing methods. So there are some limitations of these bisection methods. So now we are going to see some of the limitations that the bisection method has. First of all, in the example, the function is of second order. Hence, there should be two roots. But we have seen that we initially guessed our boundary to be 1 and 4. So we would get just one root of our first try. So if we try the bisection method and we assume a certain boundary, at the end of the process we would get a single root. So if we need to find out another root or other roots, then we need to change our boundary definition from the first iteration and recalculate the whole procedure again. So in this case, what we see that if the roots are very much farther, that means if they are situated at far locations, then what we would have in that, even if we change our boundary definitions, we would converge to the same root again. So that's the main limitation of bisection method, that we would converge to the same root if we change the boundary method. So although this is not always the case, since in some cases the roots are very much closely located. So if we change the boundary definitions, we would get the other root as well. But since these type of cases can happen in practical examples, so that's what we have said, that we need to change our boundary definitions. Also in bisection method, we cannot determine the similars because we do not know if at that point the function, if at that point the roots are similar roots or not. Although it is actually possible if we think about this. So that's the limitation, that we cannot determine the similar roots. So that is one more limitation of the bisection method. Also, what we see in that whenever we approximate our new root, we take the mean of the boundary. That means the mean of lower boundary XL and the upper boundary XU. We do not take into account the magnitudes of f of XL and f of XU. So it might happen that in some of the cases, practically, the function value at one point is much lower or very much higher than the function value at another boundary. So we, in bisection method, we do not take into this account. As a result, there is going to be a large, sometimes there are going to be cases that a large number of multiplicative results happen. So in that cases, if we truncate the results, there would be truncation error or round off errors that might happen. So in this lesson, we have learned about the bisection method. We have seen how we apply the bisection method to find out the roots of the equation. We have also practically solved a function through iterations and seen how the error percentage gets lower and lower when you calculate further. Also, we have seen the limitation of bisection algorithm. So that's it for our current lesson. So please try out the MATLAB code that I have attached with this lesson. So open your MATLAB, try out the code, and try to find out what each of the code, each of the lines means. So try to get to the root of the code. So please try out that MATLAB code in your MATLAB at home. So in the next lesson, we will see another bracketing method, which is called the false position method. So till then, thank you so much.